Hey, my name's Luke Monington, and today we're going to be talking about one of the most groundbreaking research papers that I've seen this year, the introduction of QLoRA. And what QLoRA does is it allows you to be able to fine-tune an LLM on a single consumer-grade GPU. This is going to completely open the floodgates to a ton of personalized, fine-tuned LLMs. So the research paper itself is actually pretty technical, so I ended up writing my own article here where I broke it down more simply and gave you a play-by-play analysis of all the major points that were introduced in the paper. I also wrote about how I think that this is going to impact the open source community. So I'm going to be reading through this paper together with you, and I'm going to be providing my commentary as we go. And I haven't actually posted this article anywhere, but if you want me to post it somewhere, just let me know in the comments below. Now let's get into it. So the launch of QLoRA and Guanaco marks a significant shift in how artificial intelligence will be fine-tuned in the future. This may be one of the year's most groundbreaking advancements, since it opens the floodgates to allow anyone, even with the single consumer-grade GPU, to fine-tune a model. Guanaco, the first model fine-tuned using this new method, demonstrates remarkable efficacy, achieving 99.3% of the performance level of ChatGPT. In prior methods, fine-tuning a large AI model required hefty computational power and expensive GPU resources, making it inaccessible to many. The model would be fine-tuned on a larger data type, and then it was necessary to undertake a process known as 4-bit quantization to run the model on a consumer-grade GPU post-fine-tuning. This process optimized the model to use fewer resources but sacrificed the full power of the model, diminishing the overall results. And pausing right there, in the past, the way that these models were fine-tuned is that they would be fine-tuned on a ton of GPUs, maybe 8 or 20 different GPUs, and it would require a ton of GPU power in order to fine-tune them. And then after they were fine-tuned in the 16-bit version, they would be quantized to the 4-bit version so that they could be used to make inferences on a consumer-grade GPU. The main difference here is that instead of needing to fine-tune the model as 16-bit in order to maintain performance, it can actually be done just as a 4-bit model, which makes it take significantly less GPU resources so that it can be run on a single consumer-grade GPU. And so QLoRA addresses this predicament, offering a win-win scenario. This optimized method allows for fine-tuning of large LLMs using just a single GPU while maintaining the high performance of a full 16-bit model in 4-bit quantization. For instance, earlier, fine-tuning a 65 billion parameter model would require the equivalent of more than 780 gigabytes of VRAM. However, with QLoRA, fine-tuning a 65 billion parameter model requires just a single 48 gigabyte VRAM GPU, a significantly more attainable requirement. And so what we're talking about here is reducing the GPU resources required to fine-tune by over 90%. This is completely remarkable. This groundbreaking achievement marks a new era in the AI space. A 65 billion parameter model was fine-tuned using the QLoRA method with a single 48 gigabyte GPU in just 24 hours, achieving a model that reaches 99.3% of ChatGPT's performance level. This feat is nothing short of revolutionary. And what's more is that the code for QLoRA, including the CUDA kernels for 4-bit training, were released and open sourced under the MIT license. To be clear, the Guanaco model family was made off of the Llama models. Those models are intended for purposes in line with the Llama license and require access to the Llama models. So the Guanaco models are not open source, but the code for QLoRA is open source. What's even better about this is that they're already integrated with the Hugging Face Transformers library. So there's already a Hugging Face notebook online that you can use as a guide in order to fine-tune your own LLMs. And if you'd like a guide on how you can use the 4-bit quantization technique introduced in this paper in order to fine-tune your own LLMs, let me know in the comments below and maybe I'll make one. So what is the impact of this going to be on the open source AI community? With QLoRA, the barrier to entry for fine-tuning larger, more sophisticated models has been significantly lowered. This broadens the scope of projects that the open source community can undertake, fostering innovation and facilitating in the creation of more efficient and powerful applications. The remarkable efficiency of QLoRA has opened the doors to a new realm of possibilities, one of which is the ability to fine-tune a 33 billion parameter model on a mere 21 gigabytes of VRAM. This suggests that such a task could be executed on a single NVIDIA RTX 3090 or 4090 GPU, both of which are commercially available graphics cards. Prior to the development of QLoRA, such a task would have required significant computational resources and infrastructure that was typically beyond the reach of most individuals. Now, this task can be carried out at home. This level of accessibility not only democratizes the field of AI research, but also sparks the potential for innovation, as more AI enthusiasts can experiment and contribute to their own development of these large language models. So really what I'm expecting to see now after this paper just dropped is a tsunami of fine-tuned LLMs that are specifically geared towards a bunch of different purposes. So now it makes it so that anyone can create an LLM and fine-tune it on any data set they want and have an LLM that is specifically really performant at their single task. And in addition, these high-performing LLMs can be 65 billion parameters or less. And with this 4-bit quantization and the double quantization technique that we'll be getting into, that means that even a 65 billion parameter model might be able to fit on one of these more powerful consumer-grade GPUs, which is really great because the two main issues with using OpenAI's GPT-4 is number one, data privacy, because you have to send your data over the internet and then it's on OpenAI's servers. So if you have any sensitive topics, any personal topics that you want to discuss with your LLMs, there's really a serious issue with privacy with using OpenAI's GPT-4. And the second advantage of using a local LLM is that you don't have to deal with the same filters that OpenAI has put on their model. So who says that OpenAI's decision on what is and isn't allowed in an LLM is the correct decision? Maybe a different filter would actually be a better filter. And so being able to run these LLMs locally would allow you to be able to find an LLM that has the proper filter that works for you. And so there's a lot more personalization that can go on here. You can think of GPT-4 as a sledgehammer because it's really powerful, but it's really broad. And what we're talking about here is having a surgical tool that's going to be very precise for your specific use case. That's the real power that we're seeing here. And so the QLoRA approach is poised to serve as a catalyst for a new era of innovation within the open source community. Developers can now create better performing models that can be fine-tuned very quickly, which will likely lead to an explosion of new models and applications. With the ability to fine-tune high-performing models using less computational power, we could see a wider variety of LLMs optimized for a broader range of tasks come to fruition. Hugging Face even released a collab notebook showing how to fine-tune using QLoRA right now. The point of this video is not to get into the code, but just so you know, there already is this collab notebook that introduces the no performance degradation 4-bit quantization techniques for democratizing LLMs for training and inference. And so it's already here and integrated with Hugging Face. So once again, let me know in the comments if you want me to go over this. Going back to the article, let's go over an overview of how it works. So QLoRA introduces several advancements to effectively fine-tune large language models. It brings forth three primary innovations. First, it introduces the 4-bit normal float data type, which is a novel approach to quantization that's engineered specifically for normally distributed data. This data type exhibits better empirical performance compared to existing 4-bit integers and 4-bit floats, optimizing the storage and processing of data. The second innovation is the introduction of double quantization. This technique essentially quantizes the quantization constants, leading to a substantial reduction in the memory footprint. Specifically, it saves an average of about 0.37 bits per parameter. For a large model with 65 billion parameters, this technique could save approximately 3 gigabytes of memory, which significantly increases computational efficiency. 3 gigabytes might seem a little bit small, but GPU VRAM is one of the most precious resources we have in terms of inferencing and also with training the models. And so being able to save something like 3 gigabytes of memory is actually pretty significant. The third advancement pertains to the use of paged optimizers, which employs NVIDIA's unified memory to mitigate the memory spikes during the processing of mini batches with extended sequence lengths. This technique helps avoid the gradient checkpointing memory overload, which could potentially hinder the smooth processing of data. We'll be getting more into this point later on in the article, but the main idea here is that typically the model gets to a point where it's doing a gradient checkpoint, and at that point, sometimes there's a spike in the amount of GPU VRAM that's used, and that spike in GPU VRAM can potentially lead to an out-of-memory error, which can completely mess up the training and inferencing of the model. And so having this new technique that automatically offloads some of the memory from the GPU onto the CPU when necessary is a really important contribution to be able to not have those out-of-memory errors anymore. And so QLoRa's efficiency paves the way for in-depth studies on instruction fine-tuning and chatbot performance at scales previously unattainable due to memory overhead. It empowers researchers to train and analyze more than 1,000 models across various instruction tuning datasets, model architectures, and sizes ranging from 80 million to 65 billion parameters. This was exemplified by the training of Guanaco. Additionally, the researchers discovered the critical role of data quality over dataset size in model performance. For example, a dataset with 9,000 high-quality samples outperformed a larger 450,000 sample dataset in chatbot performance. Moreover, they found no direct correlation between a model's performance on the massive multitask language understanding benchmark and the Vicuna chatbot benchmark, implying that dataset suitability is task dependent. And so this goes back to some of the points that I've been talking about in prior videos, where really what we're seeing in 2023 is that the advancements in the model performance aren't really coming from new architectures, but instead they're coming from having a better high quality data set or having more data in general. In this case, they're showing that significantly less data is actually more powerful as long as the data is much more high quality. To evaluate the model performance, they employed a tournament-style benchmarking system where models compete against each other in producing the best response for a given prompt. The winner is determined by either human annotators or GPT-4. Despite broad agreement between human and GPT evaluations on the rank of model performance, discrepancies were noted, underscoring that model-based evaluation, albeit a cost-effective alternative to human annotation, also has its limitations. And I want to actually tie this back to some of the points that I was talking about in that recent OpenAI research paper where they were using GPT-4 to actually explain the individual neurons in GPT-2. They were experiencing the same thing where, although GPT-4 was able to come up with these explanations, having a fully automated system for using GPT-4 to explain the individual activations and then using GPT-4 to judge the performance of those activations led to some concerns that possibly GPT-4 is able to understand the explanations, but maybe the explanations aren't human understandable. And so the same thing is going on here. And one thing to note is that with that OpenAI research paper, what they ended up doing to improve the performance is to take advantage of GPT-4's emergent ability of reflection. And by using reflection, they gave GPT-4 the ability to reflect on its current answers and make a revision to possibly get a better performing model. And so I'm surprised they didn't actually try taking advantage of that in this research paper, but maybe that's a topic for further research in the future. Next, let's go into some of the background before we dive really deep into those three main points that were introduced in this paper. First, what is quantization? Quantization is a process that involves reducing the amount of data required to represent an input. This is typically achieved by converting a data type with a high bit count into a data type with a lower bit count. For instance, a 32-bit floating point number might be converted into an 8-bit integer. This process helps manage the range of the lower bit data type more effectively by rescaling the input data type into the target data type's range using normalization. And so the advantage of quantization is that instead of each parameter taking up 32 bits of space, instead the parameter is taking up 8 bits of space or 4 bits of space. And when you have millions or billions of parameters, that really adds up to a lot of space. And so the idea here is that the larger data types, like a 32-bit data type, may have a different range than a smaller data type like a 4-bit or an 8-bit data type. And so what we need to do in order to convert the larger data type into the smaller data type is that we need to somehow scale it or normalize it so that it fits neatly into the 4-bit data type. And the way that we scale and normalize it actually does have an impact on the performance of the model. And so that's why they introduced a new data type in this research paper. And so to illustrate, suppose we're looking to quantize a tensor from a 32-bit floating point to an 8-bit integer, which has a range of negative 127 to 127. The conversion would use a quantization scale or constant to accomplish this. Dequantization is simply the reversal of this process, turning the quantized back into its original form. The idea here is that in order to do that conversion from the larger data type into the smaller data type, they require something called a quantization constant. And this is a constant that can be used in order to convert it back and forth between its quantized state and its dequantized state. But the issue is that this quantization constant itself takes up space. And so while the quantization process does reduce the amount of space that's taken up, there is some potential to even reduce that even more. Also, a problem that arises with this technique is that it can be skewed by outliers or large magnitude values in the input data. These outliers can cause the quantization bins, which are specific bit combinations, to be used inefficiently. This can lead to some bins being populated with few or no numbers, essentially wasting computational resources. To address this issue, a common approach is to split the input tensor into several smaller chunks or blocks, which are independently quantized. Each of these blocks would have its own quantization constant, ensuring a more efficient usage of the quantization bins. This method, known as blockwise k-bit quantization, is more resistant to outliers and can lead to a more efficient computation and better performance when processing large data sets. So the idea here is that they're adding a mechanism in order to handle those outlier values because the outlier values do oftentimes contain a lot of important information. And so we want to be able to retain that information while we do this conversion. Next, let's go through the background of what a low-rank adapter is. The concept of low-rank adaptation, or LoRa, is a significant contribution to the field of natural language processing. It's a technique particularly useful when working with large-scale language models like GPT-3 175B. The standard practice is to pre-train these models on a general domain and then fine-tune them for specific tasks or domains. However, as the models get larger, fine-tuning every parameter becomes less practical and more resource-intensive. This is where LoRa comes in. Instead of fine-tuning all of the parameters, LoRa keeps the pre-trained model weights frozen and introduces trainable rank decomposition matrices into each layer of the transformer architecture. This substantially reduces the number of parameters that need to be trained for downstream tasks. The idea here is that instead of fine-tuning all the pre-trained parameters in a really large model and instead inject a trainable matrix in between each of the layers, then that's going to significantly reduce the amount of parameters that we need to calculate gradients on. And since the main reason that we need so much memory in order to fine-tune the models is to calculate these gradients, that means that by calculating way fewer gradients that we're going to use significantly less VRAM. And so to put it into perspective, LoRa can decrease the number of trainable parameters by up to 10,000 times and reduce GPU memory requirements by 3 times compared to the conventional fine-tuning approach. What's more impressive is that it achieves this while maintaining or even surpassing the model performance and quality. Taking this a step further, LoRa uses a small set of trainable parameters, often referred to as adapters, while the main model parameters remain fixed. The gradients generated during the training phase are channeled through the fixed, pre-trained model weights to the adapter. The adapter, in turn, gets optimized to improve the loss function, enhancing the model's performance on the task at hand. LoRa also adds a twist to this process by introducing an additional factorized projection to the existing linear projection. This creates a new component in the projection equation that is highly adaptable to the task at hand, providing further efficiency in the fine-tuning process. Thus, LoRa is a promising approach when it comes to refining large language models for specific tasks. Next, let's introduce the idea of the memory requirement for parameter-efficient fine-tuning. LoRa is a methodology known for its highly efficient use of memory when it comes to fine-tuning large language models. This is primarily attributed to the minimal memory footprint of LoRa's unique components, the adapters. What's worth noting is that we can increase the number of adapters in use to enhance the model performance without significantly escalating the total memory consumption. When training an LLM using LoRa, the vast majority of memory during the training is consumed by the activation gradients and not by the LoRa parameters. This means that the usage of more adapters won't drastically inflate the overall memory needed for training. This capacity to accommodate more adapters without substantial memory escalation is key in maintaining high-quality performance comparable to 16-bit precision models. So this is just driving the point home that the actual adapters that are injected into LoRa actually aren't what's taking up all the GPU memory. What's taking up the GPU memory is calculating the gradients. And so increasing the amount of adapters actually improves performance without significantly increasing the amount of GPU VRAM that's used. This is actually a critical concept and what makes this paper so powerful. By taking advantage of this concept, they're actually able to find a way to get the 4-bit fine-tuning to have the same performance level as the 16-bit fine-tuning. And so now let's get into the 3 main techniques introduced in QLoRa. The first is the 4-bit normal float quantization. The normal float data type extends a technique known as quantile quantization. Simply put, quantile quantization aims to divide a dataset or tensor into equal parts referred to as bins. Calculating these precise bins can be computationally heavy, so shortcuts known as fast quantile approximation algorithms are often employed. However, these shortcuts might misjudge extreme values or outliers, which frequently hold significant importance. An efficient way to calculate these bins can be employed when data comes from a fixed pattern distribution. In such instances, it's more feasible to calculate the precise bins. Neural network weights, when pre-trained, typically follow a fixed pattern, a zero-centered normal distribution. All of these weights can be fit into a single fixed distribution by scaling, such that the distribution perfectly fits the range of the chosen data type, in this case from -1 to 1. In essence, this process standardizes the weights to match the same pattern as the data type. Next, the bins of the normal distribution are estimated to produce the quantile quantization data type. and these bins and weights are adjusted to fit between the -1 to 1 range. When they're in the same range, standard quantization can be applied. One limitation of this method is that it doesn't accurately account for zero values, which are crucial for padding and other zero-valued elements. To address this, a new data type is created by separately splitting the negative and positive values and then merging these sets, ensuring to remove one of the two zeros that appear in both sets. This process results in the creation of a k-bit normal float data type. The k-bit normal float data type is designed for a zero-centered, normally distributed data and guarantees that each bin contains an approximately equal number of values. So this is a really innovative concept that takes advantage of the properties of pre-trained neural networks in order to scrape out additional efficiency gains. Next is the idea of double quantization. Double quantization is a method designed to minimize memory usage by quantizing the values used in the quantization itself, known as the quantization constants. The process becomes essential when dealing with low-bit quantization, where smaller block size is crucial for precision, but at the same time leads to substantial memory overhead. So the idea here is that by converting from the larger data type to the smaller data type, you need some type of quantization constant. But the quantization constant itself ends up taking space. So if there's a way that we can reduce the amount of space that's taken up by the quantization constants, then we can get an even bigger reduction in the amount of GPU VRAM usage that we're seeing. And so consider a situation where you're using 32-bit quantization constants with a block size of 64. Here, each parameter would consume an average of 0.5 bits. To reduce this, double quantization applies another layer of quantization to these constants. So how does double quantization work? In the first step, the quantization constants from the first quantization are treated as input to the second quantization. The outcome of the second quantization yields the quantized quantization constants, as well as another set of quantization constants. The second quantization applies an 8-bit float with a block size of 256. This does not lead to any significant loss in performance, aligning with previous findings. Given that these constants are positive, the mean is subtracted before the second quantization to center the values around 0, enabling symmetric quantization. This two-step process significantly reduces the memory footprint per parameter. For a block size of 64, the memory usage drops from 0.5 bits per parameter to approximately 0.127 bits per parameter, a reduction of 0.373 bits per parameter. Thus, double quantization effectively optimizes memory usage in the quantization process. And so just to give you an idea of how big that is, that's about a 75% reduction in the space used per parameter. Next is the idea of paged optimizers. Paged optimizers involves grasping the functionality of the NVIDIA Unified Memory feature. This tool behaves as a mechanism to control memory traffic. In instances where a GPU is reaching its memory capacity during data processing, this feature intervenes. It automatically transfers data between the CPU and GPU, effectively averting memory-related issues. This mechanism resembles the process in which a computer shuffles data between its RAM and disk storage when facing low memory scenarios. Paged optimizers harness this feature. So when GPU memory reaches its limit, optimizer states are temporarily relocated to CPU RAM, freeing up space on the GPU. These states are then reloaded back into the GPU memory as needed in the optimizer update step. So this is essentially taking a concept that we already had with the CPU and the disk and extending that to be able to be used between the CPU and the GPU. Finally is the idea of QLoRA. QLoRA is a method for efficiently processing data in AI models. It works with a single layer in the base model that's been simplified and uses an adapter known as LoRa. The idea is that there are two data types, a storage data type, which is usually a 4-bit normal float, and a computation data type, a 16-bit brain float. The storage data type is where the data is kept when it's not being used, like a garage for a car. It's been simplified and uses less memory, but it's not quite ready for use yet. The computation data type, on the other hand, is the data in its ready-to-use state. When the data is needed for a task, such as during the forward and backward pass, it's converted from the storage data type to the computation data type. However, only the LoRa parameters weight gradients, which use the 16-bit brain float, are computed. This computation process involves a step of dequantization, which is essentially converting the simplified data back into a more usable form. So the key takeaway here is that in order to save GPU VRAM, we're actually storing the model on the GPU VRAM in the 4-bit quantized state. But then when we actually want to use it to make calculations, we convert it to the 16-bit quantized state. So that way we can take advantage of the performance of the 16-bit calculations while still having the space advantages of the 4-bit quantized state. So can QLoRA match the performance of full model fine-tuning? And so they ended up doing an experiment. And the experiments employed three different architectures, the encoder-decoder, and the decoder only, and compared QLoRa with the 16-bit adapter fine-tuning with the full fine-tuning for models of up to 3 billion parameters. The evaluations utilized diverse datasets and model architectures, also considering the benefits of normal float 4 over the 4-bit data types. So one of the key findings was that using LoRa on all transformer layers is necessary to match 16-bit performance. Also, it was found that the default hyperparameters for fully fine-tuned baselines are generally undertuned, suggesting room for optimization. The 4-bit normal float data type was observed to perform better than the 4-bit floating point. The setup involved evaluating different models of sizes ranging from 125 million to 65 billion parameters with different data types. It was noted that the normal float 4 improves performance significantly over the float 4 and the int 4, and that double quantization reduces the memory footprint without affecting performance. And so note here that they did test the 4-bit normal flow data type all the way up to models of 65 billion parameter size, and it did perform pretty much the same. And so interestingly, the 4-bit QLoRa was found to match the performance of the 16-bit full fine-tuning and the 16-bit LoRa. This suggests that the performance loss from imprecise quantization can be entirely recovered through adapter fine-tuning after quantization. And so what I'm saying here is that the conversion from 16 bits down to 4 bits through quantization actually does cause a little bit of a loss of data. However, whatever loss in data actually occurs can be recovered through the fine-tuning process using LoRa. So it doesn't actually cause a loss in performance. And so, in conclusion, the results consistently showed that 4-bit QLoRa with the normal float 4 data type matches the performance of the 16-bit full fine-tuning and the 16-bit LoRa fine-tuning on well-established academic benchmarks. Additionally, the normal float 4 was found to be more effective than the floating point 4, and double quantization didn't degrade performance. The findings suggest that with a given fine-tuning and inference resource budget, it might be beneficial to increase the number of parameters in the base model while decreasing their precision. Future research can delve into the exact trade-offs between the performance and the precision in QLoRa fine-tuning. So the idea here is that a bigger model generally gets better performance even with less precise parameters. Next, let's compare the models. And so this was done with a different experiment. The data used for this experiment comes from the 8 recent instruction following datasets chosen to provide a broad array of language variations, data sizes, and licensing parameters. These include datasets created by crowdsourcing, models trained to generate instructions, aggregated corpora, and hybrid datasets. The selection provides a comprehensive testing ground for QLoRa. The training setup was designed to eliminate potential biases from differing training objectives. Therefore, QLoRa fine-tuning was carried out using a cross-entropy loss function for supervised learning, even for datasets that provided human evaluations or different responses. This approach ensured consistency in training across all datasets. When a clear distinction existed between instruction and response within a dataset, only the responses were fine-tuned. In the case of two specific datasets that offered multiple responses, the top response was chosen from each level of the conversation, and the entire conversation was fine-tuned, instructions included. In all the experiments, a version of QLoRa that uses 4-bit normal float with double quantization was utilized. This version also employs paged optimizers to mitigate memory usage spikes during gradient checkpointing, optimizing the memory management during training. As the model size increased, some hyperparameters like the learning rate and batch size were adjusted for effective fine-tuning. The performance of the QLoRa trained models was then compared with the existing research-based and commercial chatbot systems. These included both reinforcement learning-based models and models that relied on proprietary data. The comparison aimed to gauge the effectiveness and efficiency of QLoRa training compared to these established systems. Then the evaluation included multiple performance metrics. One of the measures used was the MMLU, the Massively Multitask Language Understanding Benchmark, which tests a model's comprehension across a diverse range of language understanding tasks. It includes 57 tasks spanning from areas such as elementary mathematics, U.S. history, computer science, law, and more. The table presents the 5-shot test accuracy, a method where the model is given 5 examples to learn from before being tested, for llama models of varying sizes such as the 7B, 13B, 33B, and the 65B, fine-tuned on different datasets using QLoRa. Apart from this, the model's generative language capabilities were also assessed. These assessments comprise both automated evaluations and human evaluations. The latter involved using queries generated by humans to assess the quality of the model responses, providing a more real-world relevant performance measure for chatbot models. However, as there isn't a widely accepted standard for this kind of evaluation in literature, a setup involving nucleus sampling with p equals 0.9 and temperature equals 0.7 was used. The models were tested on 2 curated datasets of queries, the Vicuna prompts, which consisted of 80 prompts from a wide range of categories, and the OASST1 validation dataset, which is a multilingual collection of crowdsourced multi-turn dialogues between user and an AI assistant. For the OASST1 dataset, all user messages in the validation dataset were selected as queries with previous conversation turns included in the prompt. This process resulted in 953 unique user queries. These two datasets, the Vicuna and the OASST1, serve as the benchmarks for the evaluation. So essentially, they're doing an experiment where they're comparing a bunch of different models that are trained on a bunch of different datasets to see how each of the models performs against each other on the two datasets, the Vicuna and the OASST1 dataset. And so the way that they evaluated it is first they used automated evaluation, which was done in a couple of ways. It evolved using an evaluation protocol. Here, GPT-4, another AI model, was used to rate the performance of the different AI systems in comparison to ChatGPT on the Vicuna benchmark. Each AI system and ChatGPT were given a query, and based on their responses, GPT-4 gave each of them a score out of 10. The AI system's overall performance was calculated as a percentage of the score that ChatGPT achieved. GPT-4 was found to be biased towards the response that came first. So to minimize this bias, the average score was reported. So this is actually really interesting. So what they were doing was they were giving GPT-4 both responses at the same time and asking GPT-4 to rate the performance of both of the responses. And GPT-4 consistently had a bias of rating the first response as better than the second response. This is just another example that we need to be aware of in realizing that these LLMs do have bias. And so we need to be very responsible when we use them. And so the second automated evaluation was through direct comparisons. The rating scheme was simplified to a three-class labeling system: best response, worst response, or tie. All of the AI systems were compared to each other on both the Vicuna and the OA benchmarks. Next, they were evaluated using human evaluation. And the reason they did that is that despite the value of automated evaluations, there were concerns about the reliability of GPT-4 ratings. To address this, a human evaluation was also conducted. The human evaluation followed the same protocol as the automated one. Human annotators from Amazon Mechanical Turk were used, with 2 annotators for comparisons to ChatGPT and 3 for pairwise comparisons. Next, in order to compare the models, they actually came up with a tournament-style competition known as an ELO rating. In this, pairs of AI systems compete to produce the best response for a given prompt. After each match, the ELO ratings for the AI systems are updated according to their performance. This is done by comparing the expected outcome of the match to the actual outcome, where a surprise result leads to a larger change in the ELO rating. To control for any order effects, this process was repeated 10,000 times with different random seeds. This way, over time, the ELO rating should represent the true skill level of each AI system. So essentially, they're giving these models an ELO rating. And the ELO rating is also used in a bunch of other contexts as well, such as chess. And so the results were that the QLoRA trained model named Guanaco 65B emerged as the top performing open source chatbot model. The Guanaco model showed competitive performance to ChatGPT, one of the leading AI models. Comparing Guanaco 65B and 33B to GPT-4, it was found that these models have an expected win probability of 30% based on ELO ratings from human annotators, which is the highest reported so far. In terms of performance relative to ChatGPT on the Vicuna benchmark, Guanaco 65B performed just behind GPT-4, achieving a performance score of 99.3% that of ChatGPT. Guanaco 33B, even though it has more parameters than Vicuna 13B, is more memory efficient due to its 4-bit precision weights, and it outperforms Vicuna 13B by 3 percentage points. Additionally, Guanaco 7B can fit on modern phones with a footprint of 5 gigabytes while scoring notably higher than Alpaca 13B. This is an interesting point as well, is that all these people are very interested in being able to get these LLMs running locally on a phone. And with this 4-bit quantization, this is getting one step closer to being able to have them running on phones. Also, one thing to note is that the results show wide confidence intervals, with overlapping performance among several models. This uncertainty is believed to be due to the unclear specification of the scoring scale. The recommendation is to use ELO ratings, which are based on pairwise judgments between human annotators and GPT-4 to circumvent this issue. It's also worth noting that Guanaco is the only top model that isn't trained on proprietary data. The next best model trained only on open source data is the Anthropic HH RLHF model, which scores significantly lower than Guanaco on the Vicuna benchmark. This reveals that 4-bit QLoRA can be highly effective, producing chatbots that rival ChatGPT. So this is a major score for the open source community because now we're getting these high performing models that are done on entirely open source data sets. It's a little disappointing that they train the Guanaco model using the llama models as base because then the Guanaco model isn't open source as well. But I'm glad that the code used to do the QLoRA is open source, so that's really going to open the floodgates to a ton of new models in the future. Additionally, Guanaco 33B can be trained on 24 gigabytes in less than 12 hours. This suggests that QLoRA tuning on specialized open source data can be a promising avenue for future research, potentially producing models that can compete with the best commercial models currently available. Finally, I want to wrap this up by talking about the notes about the evaluation. There was moderate agreement among human annotators, but it was even lower when comparing strong systems, which indicates limitations in the current evaluation protocols for chatbots. Subjective preferences come into play, making it hard to agree on the better responses. To address this, future work could take insights from disciplines like human computer interaction and psychology that deal with subjective preferences. An interesting note on this point is that as we get models that get better and better, soon we'll have models that have superhuman performance. And so, how are we going to have a human be able to score the performance of a superhuman output? Is there a point where humans stop becoming a valid metric for being able to score the performance of these models? That's going to be really interesting to see in the coming years. Finally, it's also observed that automated evaluation systems have biases. For instance, GPT-4 gave higher scores to the system mentioned first in its prompt. Additionally, GPT-4's scores for its own outputs were significantly higher compared to human beings. These findings suggest that automated systems and human evaluators may have different preference standards. Therefore, future studies need to look into the potential biases in automated evaluation systems and find ways to mitigate them. That's all for this video. I hope you enjoyed. If you want to see more of this type of content in the future, please consider subscribing. And I'll see you all in the next one.